The morning of January 5th, 1943. The Solomon Islands, Southwest Pacific. USS Helena, a St. Louis-class light cruiser, cuts through dark water under a moonless sky. On the bridge, radar operators track something approaching Japanese aircraft, coming in low and fast from the direction of Rabaul. General quarters sounds. Gun crews race to their stations, but tonight, something is different. Tonight, for the first time in human history, American 5-inch guns are being loaded with shells that contain a secret so valuable, so closely guarded, that even most of the men handling them don't know what makes them special. The shells look almost ordinary. Same size, same weight. But painted around each fuse, the business end that makes the shell explode, are distinctive colored bands, red and yellow. The gunners have been told only this: handle them carefully, fire them as ordered, and ask no questions. What they don't know is that inside each fuse, smaller than a perfect coffee thermos, is a complete radio transmitter and receiver, powered by a reserve battery, built around vacuum tubes so precisely engineered they can survive 20,000 times the force of gravity and still function perfectly. What they don't know is that these shells don't need to hit anything to kill. They only need to get close. This is the story of how a device born from desperation, engineered through what seemed like impossible specifications, and deployed in absolute secrecy, transformed artillery from an area weapon into a precision killing tool. This is the story of the VT fuse, the proximity fuse, and how 20,000 G-rated components turned every American artillery piece into something the Japanese and Germans had never anticipated and could never adequately counter. But to understand why this matters, why this tiny device changed warfare as fundamentally as radar or the aircraft carrier, we need to go back to where it started, not in America, but in Britain, in the desperate summer of 1940, when the Luftwaffe owned the skies and British gunners were learning a terrible truth about the limits of their weapons. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. August 1940. The Battle of Britain rages in the skies over southern England. Every day, sometimes twice a day, formations of German bombers cross the Channel, escorted by fighters, targeting British airfields, factories, and cities. On the ground, British anti-aircraft batteries fire upward into the sky, trying to create a curtain of exploding steel through which German aircraft must fly. The mathematics are brutal and unforgiving. For every German aircraft destroyed by anti-aircraft fire, British gunners expend an average of 20,000 shells, 20,000. Each shell costs money to manufacture, requires propellant and explosive filler, must be transported to the gun site, loaded and fired. Each shell represents industrial capacity, raw materials, labor hours, and 99.99% of them explode uselessly in empty air, harming no one, accomplishing nothing. The problem is not the guns themselves. British 3.7-inch and 4.5-inch anti-aircraft guns are mechanically sound, well-manufactured pieces of artillery. The problem is the fuse, specifically the mechanical time fuse that has been standard equipment since the First World War. The principle is simple. Before firing, a gunner estimates how long the shell will take to reach the altitude where enemy aircraft are flying. He sets a mechanical timer on the fuse, essentially a clockwork mechanism which begins counting down the moment the shell is fired. When the timer reaches 0, it triggers the detonator, and the shell explodes. In theory, if the estimate is correct, the shell explodes near the aircraft, and shrapnel does the rest. But in practice, the system fails constantly. Aircraft don't fly in straight lines at constant speeds. They maneuver, they climb, and dive. The wind affects shell trajectory. Temperature affects propellant burn rate and thus muzzle velocity. Humidity affects air density. A bomber that appears to be at 15,000 feet might actually be at 14,000 or 16,000. An estimate off by just 1 second translates to hundreds of feet of error. The shell explodes too early or too late. The aircraft flies through unscathed. The gun crew reloads and tries again. And again. And again. Some shells fail to explode at all. A mechanical time fuse is a complex device, full of small gears and springs that must function perfectly under extraordinary stress. When an artillery shell is fired, it experiences acceleration forces of thousands of Gs, thousands of times normal gravity, in the fraction of a second it takes to travel down the barrel. These forces can jam mechanisms, break springs, or simply cause the timing to be off. Dud rates of 5 to 10% are considered normal. That means 1 in every 10 or 20 shells fired simply doesn't work. It falls to earth unexploded, a hazard to civilians below and a complete waste of resources. British scientists and military planners understand they are losing a war of attrition in the air. German industry is producing bombers faster than British fighters, and anti-aircraft guns can shoot them down. The Luftwaffe is systematically destroying British airfields and aircraft factories. If this continues, Britain will lose air superiority. If Britain loses air superiority, invasion becomes possible. Everything depends on finding a better way to shoot down aircraft. And in the summer of 1940, a small group of British scientists believe they have an answer. Not a better mechanical timer. Something entirely different. What if, instead of trying to predict where an aircraft will be, you could build a fuse that knows when it's close to the aircraft? A fuse that senses the target's presence and detonates automatically at the optimal distance. The concept is called a proximity fuse. In theory, it's simple. In practice, it requires solving a series of engineering problems that many experts believe are unsolvable with 1940 technology. You need a radio transmitter small enough to fit inside an artillery shell. You need it to be rugged enough to survive the violence of being fired. You need a power source that will work reliably under those conditions. You need all of this to cost little enough that you can put it in every shell, because artillery is fundamentally a weapon of mass fire, and you need it to work, every time. Because gunners need to trust their weapons absolutely. Britain has the theoretical knowledge to design such a device. British scientists are world leaders in radio technology and electronics. But Britain, in 1940, does not have the industrial capacity to manufacture millions of these devices while simultaneously fighting a war for national survival. British factories are building fighters, bombers, tanks, ships. There is no spare capacity for a massive expansion into precision electronics manufacturing. What Britain does have is an alliance with America, which has factories, resources, and engineering talent in abundance, and which is not yet at war. In September 1940, the British Tizard mission arrives in Washington. Named after its leader, Sir Henry Tizard, this delegation brings with them Britain's most closely guarded military secrets, the cavity magnetron that makes effective radar possible, details of jet engine development, research on nuclear fission, and the theoretical specifications for a proximity fuse. The Americans are interested. Very interested. The National Defense Research Committee, a newly formed organization designed to coordinate military research, assigns the proximity fuse problem to Section T, the section responsible for developing new fuses and detonators. Section T is headquartered at the Johns Hopkins University Applied Physics Laboratory in Maryland, led by a physicist named Merle Tuve. Tuve is 40 years old, methodical, brilliant, and relentlessly practical. He understands that his team has been handed a project that will either revolutionize warfare or fail completely. There is no middle ground. Either you build a proximity fuse that works reliably, or you've wasted time, money, and effort on an interesting but useless gadget. Tuve assembles a team of engineers, physicists, and technicians. He gives them the British specifications and one clear mandate: make it work. The first major decision is what kind of sensor to use. A proximity fuse needs to detect the presence of a target without physical contact. Several technologies are theoretically possible. You could use a photoelectric cell, a device sensitive to light that triggers when the shadow of an aircraft blocks sunlight. But this won't work at night, or in clouds, or if the shell is spinning in a way that the sensor doesn't happen to be pointing at the target. You could use an acoustic sensor. listening for the sound of aircraft engines. But aircraft engines are loud, and the sound could trigger the fuse too early. You could use a magnetic sensor, detecting the steel mass of an aircraft. But this requires the shell to pass extremely close within a few feet, which defeats the purpose. The only technology that offers reliable detection at useful ranges is radio. Specifically, a small radio transmitter that continuously broadcasts a signal. When that signal bounces off a nearby object, an aircraft, or later, the ground, some of it returns as an echo. A receiver in the same fuse picks up this echo. As the shell approaches the target, the echo gets stronger. When the echo reaches a predetermined strength indicating the shell is at the optimal distance from the target, the fuse triggers the detonator. This is the principle of radar, but miniaturized and simplified almost beyond recognition. Building this device requires solving problems that seem, in 1941, nearly impossible. First problem, the vacuum tube. Every radio in existence in 1941 uses vacuum tubes, glass bulbs containing a partial vacuum, and carefully arranged metal elements that control the flow of electrons. Vacuum tubes are the transistors of their era, the fundamental building blocks of electronics. But vacuum tubes are fragile. They contain thin wires, delicate grids, glass envelopes that crack under stress. Drop a radio, and you'll probably break a tube. Fire a radio out of a cannon at 2,000 feet per second, and you'll turn the tubes into glittering powder. Tuve's team needs vacuum tubes that can survive 20,000 Gs of acceleration. No such tube exists. Engineers begin designing from first principles. The tube must be tiny, no more than an inch tall. The elements inside must be robust, thick enough not to bend or break, yet precise enough to function as radio components. The glass envelope must be thick enough to resist shattering, yet thin enough to keep weight down. After months of trial and error, multiple manufacturers produce prototype tubes. They're tested by firing them in artillery shells at proving grounds. Most shatter. Some survive physically but stop functioning electrically. The engineers iterate. They try different glass compositions. They try different methods of mounting the internal elements, using springs to absorb shock, using rigid mounts that distribute force evenly. Slowly, over hundreds of tests, they develop tubes that reliably survive firing. These tubes don't look like normal vacuum tubes. They're squat, thick-walled, overbuilt, but they work. Second problem, the battery. The fuse needs electrical power to operate. In 1941, there are no batteries that can survive being fired from a gun. Standard batteries use liquid electrolytes, which would splash around under acceleration, causing short circuits or breaking internal connections. Dry cell batteries are more robust, but still contain structures that fail under extreme force. And there's another issue. The fuse cannot be powered up until after it leaves the gun barrel, for safety reasons. If a live fuse were to malfunction while still in the gun, it could detonate the shell prematurely, killing the gun crew. The solution is called a reserve battery. The battery is manufactured in an inactive state, with its chemical components separated. When the shell is fired, the acceleration force causes a physical mechanism to break a seal, allowing the components to mix. The battery activates within milliseconds. By the time the shell leaves the barrel, the fuse is powered and operational. Engineers develop and test dozens of battery designs, looking for the combination of chemistry, mechanical design, and packaging that will work reliably. Third problem, the safety mechanism. Even with a reserve battery, the fuse needs multiple layers of protection against accidental detonation. It must not arm until it has left the barrel, traveled a safe distance from the gun, and reached a predetermined point in its trajectory. The solution uses the shell's spin. When fired from a rifled barrel, an artillery shell spins rapidly, hundreds of revolutions per minute. Centrifugal force from this spin is used to withdraw safety pins, release springs, and close electrical circuits. Only when all these mechanical steps have completed, in the correct sequence, does the fuse become live. If any step fails, the fuse remains safe. This mechanical sequencing is tested exhaustively, because the consequences of failure are catastrophic. Fourth problem: size and weight. Everything, transmitter, receiver, amplifier, battery, detonator, safety mechanisms, must fit into a standard fuse cavity. This cavity is funned, roughly 4 inches tall and 2 inches in diameter. Every component must be miniaturized beyond anything previously attempted. Engineers design circuits printed on ceramic wafers. They use the smallest capacitors and resistors available, and when those aren't small enough, they have manufacturers create custom components. Weight is critical because adding weight to the fuse changes the shell's ballistic properties. Gunners rely on published firing tables that tell them what elevation and charge to use to hit a target at a given range. If the new fuse makes the shell significantly heavier, all those firing tables become inaccurate. The engineers have a weight budget measured in ounces. Every component is weighed, evaluated, and often redesigned to save fractions of an ounce. Fifth problem: reliability. None of this matters if the fuse doesn't work consistently. A dud rate of 10% acceptable for mechanical time fuses is not acceptable here. The proximity fuse is more expensive. It's more complex. If it doesn't work significantly better than what it replaces, there's no point using it. The target reliability rate is set at 95%. Out of every 100 fuses fired, 95 must function as designed. This requires not just good design, but also rigorous quality control in manufacturing, extensive testing, and constant refinement based on field data. By the summer of 1942, after thousands of component tests, hundreds of test firings, and countless design iterations, the team at Johns Hopkins has functional prototype fuses. They are designated VT fuses, officially variable time, though everyone understands this is a cover designation. The real meaning is proximity. Early test firings are conducted at the Dahlgren Naval Proving Ground in Virginia. Shells equipped with VT fuses are fired at drone aircraft radio-controlled target planes flying over the Potomac River. The results exceed expectations. Shells detonate when they pass within lethal range of the target. The drone aircraft are shredded by shrapnel. In test after test, the fuses work. Engineers and military observers watch through binoculars and see the future of artillery. But a successful test is not the same as a combat-ready weapon. The VT fuse must be manufactured in massive quantities, millions of units. It must be robust enough to withstand not just firing but also months of storage in ships' magazines, exposure to salt spray and humidity, rough handling by tired crews in combat conditions. The shell must be safe enough that ordinary sailors and soldiers can handle it without special training. And critically, the fuse must be kept secret. If the enemy captures an intact VT fuse and reverse engineers it, the advantage disappears. Worse, the enemy might develop countermeasures, radio jamming, special shielding on aircraft, tactics designed to exploit any weakness in the system. In late 1942, production begins. Multiple manufacturers are brought into the program: Eastman, Kodak, Crosley, RCA, Sylvania. Each company produces specific components. Final assembly is done at dedicated facilities under strict security. Workers are told they're building special radio tubes for unspecified military use. They don't know they're making fuses. They don't know what the fuses are for. Compartmentalization of information is absolute. Even in the military, knowledge of the VT fuse is restricted to officers with a need to know. The shells themselves are marked with colored bands, red and yellow, for anti-aircraft use, but no documentation explains what those colors mean. By January 1943, enough VT fuses have been produced to begin combat trials. The Navy is chosen for the first deployment, for a specific strategic reason. Naval battles happen over water. If a shell fails to explode and falls into the ocean, it sinks. The fuse is unrecoverable. The enemy cannot capture it, cannot study it, cannot learn its secrets. For 2 years, this rule will be absolute. VT fuses may be used over water only. Their use over land, where duds could fall into enemy hands, is strictly forbidden. Naval commanders are briefed on the new weapon. They're told that the fuses are highly classified, that their use must be reported through special channels, that any dud that lands on friendly territory must be recovered and secured immediately. The consequences of losing the secret are made clear. Use them carefully. Use them only over water, but use them, because we need to know if they work. USS Helena receives the first shipment of VT-fused 5-inch shells in late December 1942. The cruiser is operating in the Solomon Islands, supporting American forces on Guadalcanal. Japanese aircraft attack constantly, usually at dawn or dusk when they're harder to see. The gunners are experienced. They've been firing mechanical time fuses for months. They know how difficult it is to hit a maneuvering aircraft. They load the new shells with colored bands and wait. On the night of January 5, 1943, Japanese aircraft approach. Radar picks them up at a distance. Gun directors calculate bearing and elevation. The command to fire is given. 5-inch guns begin firing. And then, something happens that the Japanese pilots have never seen before, that no one in combat has ever seen before. The shells begin exploding in mid-air precisely when they pass near the aircraft. Not randomly, not occasionally, but consistently. Shell after shell detonates at the optimal distance, creating lethal clouds of shrapnel. The Japanese pilots have learned, through bitter experience, to evade anti-aircraft fire by maneuvering violently, diving, climbing, turning. But maneuvering doesn't help. The shells don't need to be aimed at where the aircraft is going. They only need to get close. And they're getting close. One aircraft is hit almost immediately, its wings shredded, spiraling down into dark water. A second aircraft attempts to climb away. A VT-fused shell detonates 30 feet above it. Shrapnel punctures the fuselage, engine, and fuel tanks. The plane catches fire and crashes. A third aircraft turns sharply, trying to break off the attack. Another airburst catches it, killing the pilot. Within minutes, the attack is over. 3 Japanese aircraft destroyed. The others flee. USS Helena's gun crews stand at their stations, shocked by what they've just witnessed. They've fired anti-aircraft weapons before, many times. They know how rare it is to actually hit anything. But tonight, they hit 3 aircraft in one engagement. The shells with the colored bands, whatever they are, however they work, are devastatingly effective. The after-action report is classified and sent immediately to Washington. Section T at Johns Hopkins reads it with intense interest. The VT fuse has passed its first combat test. Over the following weeks and months, more reports arrive. USS Helena and other ships, equipped with VT fuses, consistently achieve better results against Japanese aircraft. The statistics are compiled and analyzed. The shells per kill ratio, the number of shells that must be fired, on average, to destroy one aircraft has dropped from 20,000 to roughly 1,000. The VT fuse has made anti-aircraft guns 20 times more effective. 20 times. This is not incremental improvement. This is a revolution. But the Navy wants more data. They want to know if the fuses work in different weather conditions, at different altitudes, against different types of aircraft. They want to know the failure rate in combat, whether duds are common, whether there are any situations where the fuses don't perform as expected. And most critically, they want to know if the secret is still safe. After every engagement, intelligence officers debrief air crews and interrogate any Japanese prisoners. Do the Japanese know about the fuse? Have they changed their tactics in response? Is there any indication they're trying to develop countermeasures? The Japanese know that American anti-aircraft fire has become more effective, but they attribute this to better training, better radar, better fire control systems. They don't know about the fuse. Meanwhile, production continues to ramp up. By the middle of 1943, American factories are producing tens of thousands of VT fuses every month. The manufacturing process has been refined and standardized. Quality control procedures ensure that defective fuses are caught before they leave the factory. The cost per unit has dropped as production volume increases. The VT fuse, which initially seemed like an expensive gamble, is proving to be economically viable as well as tactically effective. And Section T continues to refine the design. Early VT fuses are designed specifically for anti-aircraft use. They're optimized to detect metal targets at the altitudes where aircraft fly. But engineers realize the same principle could be applied to other uses. What if you designed a fuse that detonates when it senses the ground? Instead of hitting the ground and exploding on impact, where much of the blast energy is absorbed by the earth, the shell would detonate 20 or 30 feet above the ground. The shrapnel pattern would be different. Instead of radiating outward from a point on the ground, shrapnel would rain down from above, reaching into trenches, foxholes, behind walls. Troops who think they're protected by cover would be exposed. This variant is designated the VT fragmentation fuse, and development begins in parallel with the anti-aircraft version. But its use presents a problem. Artillery battles happen over land. Shells fired over land fall on land. Duds will be recoverable by the enemy. The secret will be lost. For 2 years, this concern dominates strategic thinking about the VT fuse. The advantage it provides is enormous, but that advantage depends entirely on secrecy. Once the enemy knows the fuse exists, they can begin developing countermeasures. They can attempt to jam the radio signals. They can redesign aircraft with radar-absorbing materials. They can change tactics. And if they capture enough intact fuses, they might be able to reverse engineer the technology and build their own. The Allied High Command makes a decision. VT fuses will not be used over land except in situations of absolute necessity, where the tactical advantage outweighs the risk of compromise. For most of 1943 and 1944, this means VT fuses are used exclusively by the Navy, exclusively over water, where duds are unrecoverable. But war has a way of creating situations of absolute necessity. December 16, 1944. The Ardennes Forest, Belgium. Winter has come early and hard to the border region between Belgium and Germany. Snow covers the ground. Fog fills the valleys. American forces holding the line here are a mix of veteran divisions resting after heavy combat and inexperienced divisions that have never seen serious action. The sector is considered quiet, a place where tired units can recover and green units can get acclimated to life at the front without too much danger. Intelligence reports suggest the Germans opposite them are weak, undermanned, incapable of major offensive action. The war, everyone believes, is nearly over. Germany is collapsing. It's only a matter of time. At 5:30 in the morning, in darkness and fog, German artillery opens fire along an 80-mile front. Hundreds of guns, thousands of shells. The barrage is the heaviest the Western Front has seen since 1940. American positions are hammered for 90 minutes straight. Then the artillery lifts, and out of the fog come German tanks and infantry. Not weak, undermanned units, but 3 entire armies, the 6th SS Panzer Army, the 5th Panzer Army, and the 7th Army 29 divisions, over 400,000 men, supported by tanks, assault guns, and what remains of the Luftwaffe. This is Operation Watch on the Rhine, Germany's last major offensive in the West. The goal is to split the Allied armies, drive to the port of Antwerp, and force a negotiated peace. It's desperate, ambitious, and for the first few days, it works. German forces smash through American lines at multiple points. Entire battalions are surrounded and forced to surrender. Communication breaks down. Commanders lose track of their units. The fog and low clouds prevent Allied aircraft from flying, eliminating the advantage in air power that the Allies have enjoyed for months. German tanks push deep into Belgium, creating a bulge in the Allied lines, which is why history will call this the Battle of the Bulge. By December 20th, the situation is critical. The German advance threatens to reach the Meuse River. If they cross the Meuse, the entire northern sector of the Allied line could collapse. American artillery units, falling back in confusion, find themselves in direct combat with German infantry for the first time in the campaign. These are not prepared positions. These are hasty defensive lines, set up wherever commanders can find favorable terrain. Artillery pieces designed to fire at targets miles away are being used at ranges of a few hundred yards. Gunners who normally never see the enemy are watching German soldiers advance through snow-covered fields. And what the artillerymen notice, very quickly, is that their standard ammunition is not as effective as it should be. They're firing high explosive shells with impact fuses, fuses that detonate when the shell hits the ground. Against troops advancing in the open, impact fuses work fine. But German infantry, veterans of years of combat on the Eastern Front, don't advance in the open. They use cover. They move through forests, along ravines, behind ridgelines, dig hasty foxholes and trenches. And when impact-fused shells explode on the ground, most of the blast energy goes upward and outward. Troops in a foxhole just a few feet away from the impact point might be showered with dirt, but otherwise unharmed. The shrapnel pattern from a ground burst is effective in a radius around the impact point, but coverage is spotty. There are dead zones, angles where the terrain shields troops from fragmentation. American commanders are desperate for any advantage they can get, and someone, somewhere in the chain of command, asks the question, what about those special fuses? The ones that have been restricted to naval use? The ones that detonate shells in the air? Would those work better against dug-in infantry? The request goes up through channels. It reaches Supreme Headquarters Allied Expeditionary Force. Shaeff faces a dilemma. Using VT fuses over land violates the standing security order. There will be duds. The Germans will capture them. The secret, that has been guarded so carefully for 2 years, will be compromised. But the alternative is potentially losing the battle, potentially watching the German offensive succeed, potentially extending the war by months. On December 20th, 1944, General Dwight Eisenhower authorizes the use of VT fuses over land, with strict conditions. They may be used only in areas firmly under Allied control, where any duds can be quickly recovered. They may be used only when tactically necessary. And gun crews are ordered to police the area after firing, to locate and secure any shells that fail to detonate. The authorization is transmitted to artillery units across the front. Shells marked with different colored bands, not red and yellow, but different codes indicating ground-sensing fuses rather than altitude fuses, are distributed from ammunition depots. Gun crews are briefed. These are special rounds. Handle them carefully. Don't ask questions. Fire them as ordered. The first. American artillery units to receive VT fuses for ground use are supporting the defense of Bastogne, the critical road junction that German forces are trying to capture. The town is surrounded. The 101st Airborne Division, along with elements of other units, is holding against repeated German attacks. Artillery support is crucial, and on December 22nd, for the first time over land in the European theatre, American artillery fires VT-fused shells in combat. The effect is immediate and devastating. Shells that previously would have exploded on the ground, creating localized blast effects, now detonate 20 feet in the air. The shrapnel pattern is entirely different. Instead of radiating outward from a ground impact, shrapnel comes down at steep angles, in a cone-shaped distribution. It reaches into foxholes. It reaches into trenches. It reaches behind walls and terrain features. Cover that would protect a soldier from ground-burst artillery provides no protection against airburst. German troops, veterans of the Eastern Front, have survived years of Soviet artillery barrages. They know how to take cover. They know how to minimize casualties. But this is something new. Their tactics, developed through hard experience, don't work. Men crouched in foxholes, certain they're safe because the shell hit 10 yards away, die from shrapnel that comes down from above. The psychological effect is as important as the physical casualties. Artillery is terrifying under any circumstances. The sound of incoming shells, the explosions, the randomness of who lives and who dies, all of this breaks down morale and cohesion. But soldiers learn to cope. They learn that if they hear the shell coming, it's going to miss them. They learn that if they're in a good foxhole, they're relatively safe. They learn the patterns. They develop rules that help them stay sane under fire. VT-fused artillery breaks those rules. Shells explode when they shouldn't. Safe. Positions aren't safe. The explosions seem to be targeting them specifically. German commanders begin receiving reports of something new, some kind of airburst capability. but they don't understand what they're facing. Is it a new kind of time fuse, more accurate than the old mechanical ones? Is it being set by better fire control? They issue orders to dig deeper, to roof over trenches and foxholes, to use overhead cover. But overhead cover is difficult to construct in frozen ground with limited time and materials. And even when it's available, the sheer volume of fire, American artillery firing thousands of shells per day, means that some shells are going to get lucky, are going to detonate at exactly the right moment to send shrapnel through gaps in the cover. American artillery commanders notice the difference immediately. Battery commanders who have been firing support missions for months see their effectiveness increase dramatically. Calls for fire that would normally require multiple fire missions, multiple adjustments to walk the shells onto target, now achieve results with the first volley. German counterattacks that might have succeeded against conventional artillery are shattered before they can build momentum. Infantry commanders report that enemy troops seem reluctant to advance under artillery fire in a way they hadn't been before. The Germans are still fighting hard, still launching attacks, but something has changed. They're more cautious, more hesitant, more aware that American artillery can kill them even when they think they're protected. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Battle of the Bulge lasts until late January 1945. The German offensive, after initial successes, grinds to a halt. American reinforcements arrive. The weather clears, allowing Allied aircraft to strike German columns. German forces, lacking fuel and ammunition, begin to withdraw. By the end of January, the Bulge has been eliminated, and Allied forces are back on the offensive. The battle costs both sides enormous casualties, roughly 80,000 American and 75,000 German casualties. But it could have been worse. Many commanders credit the VT fuse with reducing American casualties and hastening the German defeat. Exactly how much is difficult to quantify, but artillery after action reports consistently show increased effectiveness when using VT fuses. And the secret? Partially compromised, but not as badly as feared. German forces do capture some unexploded VT fuses. They send them back to Germany for analysis. German scientists examine them, photograph them, attempt to understand how they work. Reports from this analysis survive in German archives. What they show is that German engineers correctly identified the basic principle, a radio proximity sensor, but couldn't replicate it. They understood what the fuse was doing, but not how to manufacture such a device. The vacuum tubes were too small, too rugged, beyond German manufacturing capability at that stage of the war. Germany in 1945 lacks the industrial capacity, the resources, and the time to develop an equivalent weapon. They know they're being hit with airburst artillery. They can't do anything about it. Japan faces the same problem. As VT fuses begin to be used in the Pacific Theater, Japanese forces encounter the same devastating effectiveness, and they're even less prepared to counter it. By early 1945, American forces are conducting amphibious assaults on islands increasingly close to Japan itself, Iwo Jima in February, Okinawa in April. Each landing is preceded by massive naval and artillery bombardments, and increasingly, those bombardments use VT fuses, not anti-aircraft fuses, though those continue to be used to protect the invasion fleet from kamikaze attacks. But ground sensing, fuses, designed to maximize casualties among defensive positions. Iwo Jima is perhaps the first battle where VT fuses are used extensively from the start. The island is tiny, less than 8 square miles, but heavily fortified. Japanese defenders have constructed an elaborate network of tunnels, bunkers, and fighting positions. They know the Americans will bombard the island before landing. They've designed their defenses to survive bombardment. Deep bunkers with thick overhead cover, tunnels that allow troops to move without being exposed, fighting positions with only narrow firing slits visible. Against conventional artillery, this works. Shells explode on the surface. The blast and fragmentation mostly dissipate against the fortifications. Defenders wait out the bombardment and then emerge to fight. But VT-Fuzed shells change the equation. They don't need to penetrate the fortifications. They detonate above them, and the shrapnel comes down at steep angles, finding gaps in the overhead cover, striking troops who think they're protected. The 3-day preliminary bombardment before the landing uses VT fuses extensively. When Marines land on February 19, 1945, they still face fierce resistance. The Japanese garrison fights almost to the last man, and the battle lasts more than a month. But post-battle assessments suggest that the preliminary bombardment was more effective than similar bombardments on earlier islands like Tarawa or Peleliu, at least partially due to the use of VT fuses. Okinawa, beginning in April 1945, sees even more extensive use. Okinawa is not a tiny volcanic island but a substantial landmass, home to hundreds of thousands of civilians and defended by more than 100,000 Japanese troops. The Japanese strategy is not to defend the beaches but to fight from the interior, using fortified positions in the island's rugged terrain. American forces land with relatively light opposition, then spend months fighting a grinding campaign against prepared defenses. Artillery support is continuous. American artillery batteries fire hundreds of thousands of shells. A significant percentage reports vary, but perhaps 20 to 30% are VT fused. The effect on Japanese defenders is both physical and psychological. Physically, VT fused artillery achieves higher casualty rates per shell fired. This is measured in after-action reports, though the metrics are imperfect. Psychologically, the effect is harder to quantify but appears in intelligence reports and prisoner interrogations. Japanese soldiers, who have been trained to endure artillery bombardment, find that their training doesn't prepare them for airburst fire. They describe the feeling of helplessness, of being targeted specifically, of having no defense. Some Japanese units begin attempting to construct overhead cover for every fighting position, but this requires time and materials that aren't always available. Other units try to adapt by staying deeper in their tunnel systems, only coming to fighting positions when American infantry is close. But this reduces their effectiveness at stopping American advances. By June 1945, when the Battle of Okinawa finally ends, American forces have fired more than 22 million artillery shells in the Pacific Theater. Not all of them are VT-fused. Standard high-explosive shells are still used extensively, and for some targets, impact fuses are more appropriate than airburst. But the proportion of VT-fused shells has been steadily increasing. Production is no longer limited. American factories are turning out VT fuses by the millions. Cost is no longer a serious concern. The industrial base is so productive that the marginal cost of a VT fuse versus a mechanical time fuse is acceptable, and effectiveness is proven beyond any doubt. The VT fuse works. It works in naval anti-aircraft use, where it was first deployed. It works in ground, artillery use, where it was initially forbidden. It works in different climates, from the frozen Ardennes to the tropical Pacific. It works against different types of targets. It simply works. After Japan's surrender in August 1945, the VT fuse is declassified. The announcement makes newspapers, though for most Americans, exhausted by 4 years of war and overwhelmed by the implications of atomic weapons, the proximity fuse is just another piece of military technology. There are press releases. There are articles in technical journals. Engineers at Johns Hopkins and the various manufacturing companies are publicly credited. The basic principle is explained. A miniature radio proximity sensor, triggered by the return echo from a target. The engineering challenges are described: the ruggedized vacuum tubes, the reserve battery, the safety mechanisms. But the public response is muted. The bomb ends the war. The proximity fuse is a footnote. Within the military, the assessment is very different. Vannevar Bush, who as director of the Office of Scientific Research and Development oversaw much of America's wartime scientific mobilization, later writes that the VT fuse is second only to the atomic bomb in terms of its impact on the war's outcome. This is not hyperbole. The atomic bomb destroyed 2 cities, and convinced Japan's leadership to surrender, but it was used exactly twice. The VT fuse was used millions of times, in every theater, against every kind of target. It made anti-aircraft guns 20 times more effective, reducing aircraft losses to both American and Allied forces. It made field artillery significantly more lethal, increasing casualties among enemy forces and reducing the number of American casualties in ground combat. It shortened battles. It saved lives, American and Allied lives, at the cost of enemy lives, which is the brutal arithmetic of warfare. Some historians argue that the VT fuse saved more lives than any other single invention of the war, including penicillin. This is difficult to prove. With statistics, causality in warfare is complex, and many factors contribute to any outcome. But the argument goes like this. Every American aircraft not shot down by Japanese anti-aircraft fire is an aircraft that survives to fly another mission. Every pilot who survives is a trained pilot who doesn't need to be replaced. Every ground attack that succeeds with fewer casualties is a unit that remains combat effective for the next battle. Over thousands of engagements, across 3 years of war, these small advantages compound. The VT fuse doesn't win any single battle by itself, but it contributes to winning many battles, and winning battles faster, and with fewer friendly casualties. The technology itself continues to evolve after the war. The basic principle, a proximity sensor that triggers a detonator, remains valid, but the implementation changes as electronics advance. Vacuum tubes are replaced by transistors. Transistors are replaced by integrated circuits. Modern proximity fuses are smaller, more reliable, more sophisticated than the 1943 originals. They can distinguish between different types of targets. They can be programmed for different burst heights. They can work in electronic warfare environments where the enemy is actively trying to jam or spoof their sensors. But the fundamental insight that a smart fuse makes every shell more effective remains as valid today as it was 80 years ago. The VT fuse also influences post-war thinking about weapons development. Before World War II, military innovation focused primarily on making weapons more powerful, bigger guns, faster aircraft, heavier armor. The VT fuse demonstrates that precision and intelligence can be as valuable as raw power. A shell that explodes at the right moment is more effective than a shell twice as large that explodes at the wrong moment. This lesson shapes the development of guided missiles, smart bombs, and precision-guided munitions. The modern military obsession with precision, with putting warheads on exact coordinates, with minimizing collateral damage, with achieving effects with fewer weapons, all traces back, in part, to the success of the proximity fuse. But perhaps the most significant legacy is industrial. The VT fuse program demonstrates that America's greatest military advantage in World War II is not any single weapon, but the ability to design sophisticated technology and then manufacture it at scale. British scientists conceive the proximity fuse. American engineers make it work. And American factories produce it by the millions, cheaply enough that it can be used in ordinary artillery shells, reliably enough that soldiers trust it completely. This integration of scientific research, engineering, development, and mass production becomes the template for American military power in the Cold War and beyond. Stealth aircraft, cruise, missiles, GPS-guided bombs all follow the same pattern. Develop the technology, prove it works, manufacture it at scale, distribute it widely, and achieve a qualitative advantage that enemies cannot easily counter. There's an irony here that deserves reflection. The proximity fuse is developed to solve a specific problem, how to shoot down aircraft more effectively. It's used for that purpose, successfully. But its greatest impact comes from an application that wasn't originally intended: ground artillery. Engineers designing the fuse in 1941 and 1942 are thinking about anti-aircraft defense. They're trying to protect ships from air attack, cities from bombing raids. The idea of using it for field artillery exists, but it's secondary, constrained by security concerns. Only when those security concerns are overridden by battlefield necessity, in the desperate days of the Battle of the Bulge, does the full potential become clear. A weapon designed for one purpose proves to be revolutionary for another. This happens often in military history. Technologies developed for one application find unexpected uses elsewhere. Radar, developed for air defense, becomes essential for navigation and fire control. The jet engine, initially used for fighters, transforms civilian aviation. Nuclear technology, developed for bombs, becomes a power source. The proximity fuse fits this pattern. But what makes it particularly significant is the speed of the transition. From first combat use in January 1943 to widespread ground use in December 1944 is less than 2 years. The identification of a new application, the authorization to use it despite security risks, the logistics of distribution, the training of gun crews, all of this happens in wartime, under pressure, in the middle of active campaigns. It's a testament to organizational flexibility, to the ability of military institutions to recognize a better way of doing things and implement it quickly. And what of the Japanese expectation, or rather, lack thereof? The title suggests that Japanese forces never expected VT fuses to turn American artillery into a death machine. This is accurate in the sense that no one in 1943 could have predicted how the technology would ultimately be used. Japanese military planners, designing their defensive strategies for the Pacific Islands, assumed they would face conventional artillery. They built fortifications based on that assumption. They trained their soldiers based on that assumption. When American forces landed with VT-fused artillery support, those assumptions proved incorrect. But it's not that Japanese commanders were uniquely blind or foolish. German commanders made the same miscalculation in the Ardennes. British commanders, facing German artillery earlier in the war, would have made the same miscalculation if the Germans had developed proximity fuses first. No one expected it, because the technology was unprecedented. There was no historical precedent for artillery that could reliably airburst over a target without mechanical timing. It was genuinely new. The more profound surprise is not that the Japanese didn't expect it, but that it happened at all. In 1940, when the British first approached American researchers with the concept, many experts believed it couldn't be done. The engineering challenges seemed insurmountable. The idea of building a radio system that could survive being fired from a gun was, to many engineers, absurd. Even among the team at Johns Hopkins, there were moments of doubt, times when test failures seemed to prove the skeptics right, when the smart move would have been to abandon the project and work on something more achievable. But they persisted. They solved problems one at a time. They accepted failures as information rather than defeat, and they succeeded in building something that transformed warfare. That persistence, that methodical approach to seemingly impossible problems, is perhaps the real story here. Not the specific technology of the VT fuse, but the process that created it. The willingness to attempt difficult things. The integration of theoretical knowledge and practical engineering. The collaboration between universities, private industry, and military organizations. The acceptance of failure as part of development. The focus on reliability and manufacturability, not just functionality. These are not uniquely American traits, but during World War II, America demonstrated them at a scale no other nation could match. The men who designed the VT fuse, Merle Tuve and his team at Johns Hopkins, the engineers at Eastman Kodak and RCA in Sylvania, and the other manufacturers, the military officers who recognized its potential and fought for its deployment, are not household names. There are no monuments to them. Their work, once classified, remains obscure even after declassification. But their legacy is embedded in every precision weapon, every smart bomb, every missile that uses proximity sensing to achieve effects. They proved it was possible. They showed how it could be done. And in doing so, they changed the nature of warfare in ways that persist to this day. When American gunners on USS Helena fired those first VT-fused shells on January 5, 1943, they didn't know they were making history. They were just doing their jobs, trying to shoot down Japanese aircraft before those aircraft could drop bombs or torpedoes. When American artillery crews in the Ardennes fired VT-fused shells at German infantry in December 1944, They didn't know they were demonstrating a revolution in ground warfare. They were trying to survive, trying to stop the German offensive, trying to protect their fellow soldiers. That's how most military innovations are actually used, not by people who understand the full historical significance, but by people focused on the immediate problem in front of them. The significance becomes clear only later, in retrospect, when historians can trace the consequences. And the consequences of the proximity fuse are clear. It made every American artillery piece, from 5-inch naval guns to 155mm howitzers, substantially more effective. It forced enemy forces to change tactics, often unsuccessfully. It saved Allied lives by ending battles faster and with fewer casualties. It demonstrated the value of precision over power, intelligence over brute force, and it established a template for military innovation that remains relevant 80 years later. Not bad for a device the size of a coffee thermos, containing vacuum tubes that cost a few dollars each, manufactured by the millions in factories across America. The Japanese never expected 000G-rated fuses to turn American artillery into a death machine. But then, neither did most Americans. Neither did most of the engineers who designed it, at least not until they saw it work. Expectations are based on experience, on what has happened before. The proximity fuse had no precedent. It was genuinely new, not an improvement on existing technology, but a fundamentally different approach to an old problem. And in warfare, as in many human endeavors, the genuinely new thing is often the most disruptive, the hardest to counter, the most decisive. That's the lesson, if there is one. Not that American technology was superior, though it was. Not that Japanese or German forces were inferior, though they lacked equivalent technology. But that innovation, genuine innovation that changes the rules, rather than playing by them, creates advantages that are very difficult to overcome. The VT fuse didn't make American soldiers braver or better trained. It didn't make American generals more brilliant tacticians. It simply made American artillery work better. And in a war where artillery accounts for a substantial percentage of casualties, making artillery work better matters enormously. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.